Every auspicious occasion begins with the lighting of lamp, a symbol of wisdom, learning, enlightenment. To embrace both tradition and technology, we now witness a digital lamp lightening ceremony marking the inauguration of this FDP.
I request Director Madam to announce digital lamp inauguration.
Okay. Firstly, since this is a smart and sustainable manufacturing, I think even the lamp has got digital. So
Yes.
how do we?
You can
It's
you please initiate start the lamp. We'll start the lamp.
yeah. You can please start the lamp.
Asit sir, please.
Sir, please start the lamp. Yeah, is it done, sir? Should I continue, sir? Yeah. Now, we have symbolically invoked wisdom and positivity to
No,
guide us through this FTP.
sorry to interrupt. It was not played actually.
It is not possible.
Please share your entire screen and then play that. I'll share that. Don't worry. Is it visible?
No, the screen.
Yes, it is visible. It is visible.
Yes, sir, visible.
Okay. Thank you, sir. With the lightening of lamp, we have symbolically invoked wisdom and positivity to guide us through this FDP. May this lamp of knowledge inspire us in all our sessions. Now, coming to the theme of this FDP aims to provide valuable insight into the latest advancements in Industry 4.0, smart and sustainable manufacturing practices, and innovative approaches to teaching and research. With a blend of expert lectures, interactive sessions, and hands on learning, we are confident that the participants will gain both knowledge and inspiration. Now, I request to give the welcome address by the coordinator, Dr. Asit Kumar Parida. Thank you, Asit sir, for sharing the details of our FTP. Now, may I request our beloved HOD sir, Dr. TVSMR Bhushan, Associate Professor, Mechanical Engineering Department, to kindly address the gathering.
Thank you. Respected Director Madam, Dr. Divya Nallagaru, respected Principal, Dr. MNV Ramesh Garu, our esteemed resource persons, fellow coordinators, and my dear faculty colleagues and participants. A very good evening, all of you. It is a great pleasure to welcome you to the inaugural ceremony of this 1 week Atal FTP program on smart and sustainable manufacturing strategies for Industry 4.0. First and foremost, I extend my heartfelt gratitude to All India Council for Technical Education and the Atal Academy for their vision and support in supporting this FTP. The Atal initiative is a crucial step towards empowering educators with the skills and the knowledge required to meet the demands of a rapidly changing academic and industrial landscape. The theme of our FDP, Smart and Sustainable Manufacturing Strategies for Industry 4.0, is not just relevant but essential in today's world. As we look at the shifts happening in industry and technology, we realize the need for a reskilling revolution in academia. The program is designed to bridge the gap between traditional teaching and cutting edge advancements, ensuring we equip our students with the skills they need to thrive in the future. This will be a week of insightful sessions, collaborative learning, and professional growth, enabling us to enhance our teaching and research going forward. To all the participants, I urge you to engage deeply with the material. The success of this program depends on your active involvement, curiosity, and willingness to learn. I would like to extend my sincere thanks to the resource persons for accepting our invitation despite their busy schedules. My thanks also to go to our college management, our director madam, principal sir, course coordinator Dr. Asit Parida, and all my faculty members who have worked tirelessly to make this event success. With these and with a great anticipation of extensive learning, I wish all the participants to have a happy and enriching learning experience. Thank you all.
Thank you, sir. Thank you for your insightful words. Now, may I request
Now it is
our
Director Madam will speak now, please.
now may I request our beloved Director Madam, Dr. Divya Nalla, to please address the gathering.
Madam, you are muted.
Yeah, good evening, everyone. I'm sorry to have got in between because I need to leave. So I just wanted to address all of you. This actually, in the current scenario of engineering education, where most of the students are getting into IT related courses, and most of them think that AI is the only one which is going to survive in the coming industry. In this scenario, there is a heavy requirement for one second. There is a requirement for people to understand what exactly is the requirement in the industry. And like in the current industry, there is a heavy requirement for people to know the domain knowledge in mechanical engineering, in manufacturing sector, and these, and also know about the latest technologies like smart manufacturing, then the integrating this, the core domains to the emerging technologies. This integration is something which is very much essential in the current scenario, and that I think this workshop is addressing that requirement. And it is a very much useful workshop, a faculty development program for all the faculty of mechanical engineering, as well as people who are really interested in uh, equipping themselves for the next industrial requirements. And then once the faculty gets to know what exactly are the requirements, what exactly are the technological advancements, then they can then shape the students accordingly. So I think this is a very useful faculty development program, and also it is like very useful for the teachers, and in turn this should result in students learning these different technologies. And uh, and for this, in these lines, actually, to train the students in smart manufacturing, and to prepare them for industry 4.0, we in our institution have started a minor on smart manufacturing, and some students from computer science are doing this minor. So that shows the integration of these different branches of engineering will definitely benefit the students in facing the industry challenges at a future stage. So thank you very much, and I would like to thank all the participants. For so many participants from all over India have enrolled in this workshop. And and I would also like to thank the Department of Mechanical Engineering for conducting this workshop, and wish them all the best. Thank you.
Thank you very much, ma'am, for your enlightening words and your sparing your valuable time for us. Now, we have with us our
Ramnath.
principal.
Thank you very much, madam, for sparing your valuable time, keeping in your hectic schedule. You have joined us and enlightened us. I would like to share another point that we have a good, successfully, we have enrolled about 151 participants in this ETL FDP program, for your information. Thank you very much, Ramna sir. Please continue.
Thank you, sir. Now, we have with us our principal, Dr. MNV Ramesh, Professor Nallamala Reddy Engineering College, who will share his thoughts on the theme of this FDP. Sir, please.
Thank you, Ramna sir, for inviting me for this 1 week FDP program. So good evening to all the dignitaries, respected resource persons, faculty, participants, colleagues, and dear students. It gives me immense pleasure to welcome you all for this Atal FDP program on theme Smart and Sustainable Manufacturing Strategies for 4.0. At the outset, I would like to thank the AICTE for sponsoring this program and giving opportunity to conduct this program at our institute. We are at a stage where digital technologies, automation, artificial intelligence, and data analytics are changing the industries worldwide. Industry 4.0 is not just a smart machines, it is about integration, intelligence, and innovation. In manufacturing, it helps industries achieve better productivity, higher efficiency, quick decision making, and global competitiveness. At the same time, the world is facing challenges like climate change, limited natural resources, environmental damage, and rising energy needs. This makes sustainable manufacturing essential. The aim is to not only to produce efficiently, but also produce responsibly. Faculty development programs such as this one, they play a vital role in preparing the educators and researchers to guide the next generation of engineers and professionals. Through this FDP, I am confident that our participants will gain insight into emerging technologies for smart manufacturing, practical strategies for implement Industry 4.0 principles, and pathways to build resilient, sustainable, and future-ready industries. Before I conclude, I would like to express my sincere appreciation to the coordinators, department HOD, resource persons, and organizing team for their dedication in bringing together this valuable program. I also thank participants to their enthusiasm and commitment to continuous learning. With this, I would like to conclude my speech and once again welcome you all for this FDP, and I wish you all make this FDP grand success. Thank you very much.
Thank you very much, sir, for your encouraging words and insightful few words about FDP. Now, the vote of thanks for this inaugural will be presented by Dr. Asit Kumar Parida. Yes, thank you, sir. With this, we conclude the inaugural ceremony. We now proceed to the first technical session of FDP. Thank you all once again. I request Dr. Asit sir to please take on the proceedings.
Sir, tell me.
Yes, Professor, I joined. Yeah, am I audible? Yeah, thank you. Just give me a minute. Can you able to see my screen? Can you able to see?
Yes, sir. Visible.
It is visible, sir.
Yeah, thank you. So thank you, Professor Parida and Department of Mechanical Engineering in particular, and the Institute for giving me the opportunity. So my group works in the area of micro nano manufacturing, exclusively into nano manufacturing. However, micro machining and micro manufacturing is one of our byproduct, or you can say that it is our one of the intermediates, because if I want to make some biomedical devices or something, I also require micro machining sometimes, and then nano manufacturing also. So looking at the program on micro manufacturing, so I am going to talk on micro nano machining using uh, biological microorganisms, which is one of the organisms that we are going to talk is acidothiobacillus peroxidans. So I work in the area of micro machining and nano finishing group. See, I work into mostly into micro nano manufacturing. Maybe applications may be different. Some may be defense, which I am not showing here, which predominantly we do for DRDL Hyderabad, RCI Hyderabad, and many other organizations, because there we do mostly into nano manufacturing. So that's why I'm not going to show as a part of this one, because respecting the time and other things. Sustainable manufacturing, where we develop the cutting fluids. The slides are there, then I will explain. Additive manufacturing is one of the nowadays core area that we are working. Smart manufacturing, where we design and develop the smart systems, and bio nanomaterials and manufacturing. Again, is one of the area where I love to work, even though I am an engineer. I try to work on bio-nano manufacturing. Mostly my research, even though I work into micro, nano, and super finishing and other things, mostly some of the applications that I look at is bio. Because, as I said, I told multiple times also, I want to become a doctor. I am from Jawahar Navodaya Vidyalaya, Kadapa. So where I completed in MBPC, maths, biology, physics, chemistry. So in the morning I have written medicine, and in the afternoon I have written engineering. But however, as you know, that medicine seat getting is very difficult. So I don't have money, or my parents don't have money to send me to the engineering. Medicine for long term and other things. So I started doing engineering. Even though I do engineering, so I want to do some of the work into biomedical. That's why I love to work in the area of biomedical. That is the background. So ultra precision manufacturing laboratory that we have at IIT Tirupati. So we have multiple groups. As I said, does only micro machining is a complete solution? So it's my personal perspective, may not be actually. Okay. So you require nano finishing also. Whenever you want to do some of the things, majority of the things maybe require finishing. Some of the things also can end up with micro machining. Okay. So where are the cases where we can do with micro machining that we can see? So various applications that we try to do. This is one of the project that we have done, and this will be just briefing. So you can see here we have a laser system at IIT Tirupati that can operate in multi modes. So we have a 200 watt nano lasers. So I mean say nano pulse lasers, and this can be operated under liquid laser micro machining. So you can have any transparent liquid, so that you can do the machining using any type of reflection and refraction based mechanisms. And so one of the beauty about this one is, for example, if you see here the first one, this is what machined the nitinol, nickel titanium alloys, for drug eluting stents and other things in a dry condition. I mean to say, there is no liquid condition. When you do under liquid laser micromachining, so you can have a barfi. So the best example is the machining using lasers is melting and evaporation. When you are melting and evaporation, what will happen? This evaporated particles will form dross, actually, dross and debris here. So if you are under liquid, what will happen when it jumps? What will happen? These particles, by the time it reaches to the surface, what will happen? It may become the particles and float away. That's why you get a very better surface compared to normal. This is one mode that we have at IIT Tirupati. Second mode that we have is a single pulse. So that means that whenever I want to do texturing or polishing of a surface using lasers, I just want to bombard with respect to a single pulse. So when I am bombarding with single pulse, for example, laser power, like 30 watt or something, what will happen? So I can understand easily that uh, what will be the depth of the crater, what will be the width of the crater. That is what gives me a clear cut idea. For that purpose, we use lasers. Lasers have its own disadvantages that I am going to talk in the upcoming slides. So next one is we have microfluidic devices and so on. So where you can have laser micro channels and other things. For this one, you require a different types of lasers. Okay. So this is one of the application that we have done using deep hole drilling EDM process. I'm giving an overview before I take you to the technology actually. So what we have done here is this rod versus 304, which is total length is around 100 or 200 length, where we want to manufacture a hole of 1 diameter with on a 16 pitch circle. Actually, there are 10 holes. You can see the cross section of these holes. So these holes need to be manufactured. Okay, this is the first and foremost project that we got when I was in IIT Guwahati. Okay, so we also work into hard materials, micro machining for fuel injector nozzles and so on. Apart from it, we also do laser coatings. Currently, I am not touching the laser coatings, laser texturing, laser coating, and other things. We also work in the area of micro nano manufacturing. But due to time constraint and other things, I am not exclusively going in. However, we do laser coatings, though I'm just explaining because some of you may be interested. That's why. So we do laser coatings, we do laser functionally graded coatings, and ceramic coatings, metal coatings, and so on. Okay, whatever the coatings that you want, using lasers, we can do. Apart from it, we also have some of the facilities like PVD, physical vapor deposition. In physical vapor deposition, we have two varieties. One is RF magnetron sputtering with a single substrate and target. Okay. So we have again a new system that we received RF magnetron sputtering with a four targets at a time. So you can bombard four materials simultaneously onto the one of the targets. So this is one, and another one is we have a DC pulsating, I think pulsating DC sputter coating. So we have these coatings also. So those people who are interested in micro coatings, why I'm saying micro coatings is whenever you want to coat any ceramic coatings or hard material coatings, in PVD system, physical vapor deposition system, predominantly you may end up in 1 to 2 in a gap of 7 to 8 hours. For example, if you want to coat orthopedic coatings for on hydroxyapatite on titanium, so normally our system take 6 to 8 hours for 1 to print. So I mean to say 1 to coat with a uniformity and other things. So that's why we are saying you that this is also come under the micro manufacturing division. At IIT Tirupati, we have DT100I. Whatever you are seeing is DT100 only. We have a DT100I, which is you are going to see in the next slide. So this is in open condition. Our system has in a closed condition. So that's why we want to show here. This has mechanical micro machining like micro milling, micro turning, micro drilling, and other things. Apart from it, it also have micro die-sinking EDM, micro EDG, that is wire EDG and wire EDM and so on. Okay, EDM milling and drilling also where tool can rotate about its axis. However, what we have at IIT Tirupati is this. Okay, this is the latest machine that we have, DT100i, which is called as an intelligent machine. This consists of whatever the processes that I have told already, like micro drilling, micro milling, micro turning, and so on. Apart from it, it also have micro iridium, micro EDG, and micro end milling. So I'm saying micro ED milling and other things. So die sinking and this, see, there is a difference between micro die sinking EDM and micro EDM milling or something. Also, what is the meaning is, in die sinking EDM, your tool will not rotate actually. So that's why these people have differentiated, saying that micro EDM milling and other things. Apart from it, so what are the two new features that the machine have, or machine can have, is laser micro machining center. It can also come up with a laser system. However, that will cost you like another, this machine worth about 3.2 crores or something. So by the time it lands in IIT Tirupati, because customs itself, it sometimes take a lot of money. So if you want to go for lasers, it will cost you again 90 lakhs or so, or at least minimum 60 to 70 lakhs it will cost. And simultaneous EDM and ECM, which is called simultaneous electrical discharge chemical machine. I'm just going to talk about that one. So this is one of the state of art uh, attachment that we have at IIT Tirupati. Those people who want to do simultaneous, because many people have their laboratory setups like simultaneous EDM and ECM, or electrochemical spark machining, or electrical discharge chemical machining. People, they say many names, means things are same. What is that advantage and other things you can see in the upcoming slides. Okay, so what we have is a commercial one. So if those people who are looking at doing a very good quality thesis or something, they can come up with our requirements. So this is the machining center that we can clearly see: micro turning, micro building. You have measurement, online measurement, micro lasers. That's what I was telling. Micro lasers is also there. Micro iridium, micro ECSM, and so on. Attachments are there. Okay, so working range, working area is 200 by 100 by 100, and EDM is, you can use both deionized water or oil, depend on your oxide layer formation or carbide layer formation. So here I'm just telling you that oxide layer formation and carbide layer formation. See, why I'm saying this is, whenever you are using EDM process, die sinking or electrical discharge milling or something, whenever you are using, your final application is required hard surfaces, then you are advised to go with oils, because oils are normally paraffin based and other these based. This will have carbon in its compounds when you are making EDM process. So there is a chance of carbides formation, which gives the machining zone to be hard. That is one of the advantage or advice that I can give you. The second advice, if you are looking for a very smooth surface, that means that you need to polish after EDM process. In that circumstances, what you need to do is, you need to predominantly use DI water, because water will have H2O. So normally what will happen is, you just get up with oxide layers. So oxide layers are very easy to clean up. That's why you are advised to go with deionized water. Because why I'm saying all these things is, many of the people who are doing research in manufacturing, that too particularly in micro machining and other things, predominantly uses electrical discharge machining or EDM process. That's why Sometimes you may be know this the fundamental difference so that you can do wonders. Okay, if I want to do post processing after EDM process, you predominantly use oxide based fluids, that is deionized water and other things. For example, your final pin process itself is EDM process, you don't want to do any other, and your requirement is also some hard surfaces, you go with carbon based oils or something. Okay, so some people also use kerosene and other things. These are all are petroleum based. So when you treat it, what will happen? So one case your oxide layer will so that you can do finishing. If you don't want, you can go with oxide based or petroleum based or carbon based oils, so that it will give very hard surfaces. That's the only suggestion that I would like to tell you. Okay, this is how our micro turning system works. So you can just touch it and you can immediately get all the details of what is the forces and other things. Normally, we try to go with very, very minute feeds and minute depth of cuts in microns, like 5, 7 microns or something. Okay, so this is the pin that you can see here before deburring and after deburring. So how the micro turning operation can be done, where you can do taper turning, where you can do step turning, where you can do all those turning operations. And this is the medical mm, pin for biomedical application, micro pin for biomedical applications and so on. Okay. So, however, when you are seeing in the microscope, this is almost all 35x. That means that the starting level of field enhanced scanning electron microscopy range, where you can do the surface morphology and understand how the deviations and other things. The only thing that you can see here is that burr formation is there, and which you need to do later the finishing process. That's why finishing also plays a crucial role in the micro machining process. Like you can see here, micro shafts of 50 diameter. I mean, say 50 microns actually, not it is 50 it is 50 microns. So you can just do the step turning operation. First, you do like you can see here, like step by step by step, and then you can do a complete. However, you can see here, being a material as a soft material copper, what you can see is there is a deviation in this one, in the shaft. So a deviation in the shaft is experienced because of mechanical action of the turning tool. Okay. However, if you want to develop a perfect shaft without any deviations, you can do EDM process. So like this, you can see the first one. So sacrificial electrode, you can put a cathode and you can have an anode and you rotate it. I said that when I was explaining you at the start, we have electrical discharge micro milling process. So what is the difference between electrical discharge micro milling and die sinking EDM or die sinking electrical discharge micro machining? Is in this case one, micro milling, electrical discharge micro milling, your cutting tool rotates. So now you just understand here that my tool is rotating. I have a sacrificial electrode which can eat away all these things. Because of that, what will happen in EDM process, I don't have mechanical contact between tool and workpiece. If there is a mechanical contact, a physical contact, you can say that then it will not work because it become a closed loop. So that's why whatever the issue that you are facing here with respect to micro turning operation, because of physical contact between the cutting tool, which is much harder than the workpiece material, and the workpiece material can be eliminated by this particular process. So this is a called block electrical discharge micro machining, where you put a block and try to rotate the tool, so that what will happen, that mechanical, whatever the EDM principle operates, will operate between the block and the tool. Okay. However, here I would like to tell you, many of the people who comes to our interviews, they say that they have worked in EDM. When we ask them explain the EDM principle, so majority of the people says when there is a potential difference between two electrodes, the spark will come and material removal will takes place. Next question, then when we ask how the spark takes place, normally some of the people may face difficulty. Okay, so how the process will work here is, you have anode and cathode. So when the work function comes, I mean to say when the applied voltage is more than required voltage to the electron release, the electrons will release, and these electrons will touch the first layer of dielectric fluid, and many electrons will produce, such that different layers of dielectric fluid, when it before it touched to the workpiece material, which is anode, so because it is attracted towards anode, okay, because of that, what will happen, first layer generate some, second layer generate few more, third layer generate few more, like that avalanche of electrons will come and hit the anode. When it hit the anode, what will happen, kinetic energy of the electrons will convert into thermal energy and spark takes place. It is not that when there is a potential difference suddenly spark will come, no. Okay, so you should understand the physics of the process, and many of you may know it, and those people or the students are who are listening, it may be useful. That's why I just tell, I'm telling the same thing. Once I made the electrode, I can check online measurement of this one. So this online measurement system is there, where you just pass the lasers and you can just check whether my tool is perfectly straight or not. That is the advantage. Okay, so that is the advantage. Second thing, you can also make high aspect ratio EDM holes and so on. So once you have, the advantage here is, you, if you see here, I have micro turning operation. I can use the same thing in terms of tool for EDM process, or I can do the block EDM process and I can use the same for drilling process. Okay, so I need not to take out the tool, so that the eccentricity problems and other problems will not be there. Okay, so now once you did all these things, you can check how the holes can be generated. See here, at a 600 magnification, this is 20, this length is 20 microns. You can see how the hole sizes are 12.5, 10.5, 8.5, on 6.5 microns. Normally, the cell dimensions will be ranging a lot. So some of the microorganisms also will be the size of 20 microns and other things. Such a cases, these filters can act, and it can act as a filters for those applications. So the disclaimer is that we have not machined it. It is the capability demonstrated by OEM, which is called micro tools. Okay. So you can see here 6.5 micro hole machined on a 50 micron stainless steel plate, probably the world's smallest hole with the highest aspect ratio. Okay. So this is what they have done it. And you can see here the microorganisms. These are much bigger than the hole sizes and other things. I was pretty much excited to see this one. This is called simultaneous electrical discharge chemical milling process. Whenever I say milling process or a micro milling process, the tool is rotating. You see here, two things are there. This is a micro electrical discharge milling, where normal EDM circuit is attached and you got the surface. So we have also simultaneous electrical discharge chemical micromilling process. Same setup, but only thing is that controllers are different and the liquids are different. Okay, so here it will be electrolyte and other things will be there. Patented electrolytes will be there. So you can just see here the surfaces are predominantly. So the basic understanding here is that it will be EDM plus ECM, and ECM will give you very good surfaces and other things. Okay, so because of that, what you can see is, so initial surfaces are almost all 142 nanometers, and when you use simultaneous EDM and ECM process, you will have 22 nanometers. Okay, so what is the application? What is the application is whenever you want to put some sensors, air can entrap or a gas can entrap here. So the entrapment of gas will be slightly less here compared to the other case. Now you can also see here, so two things are developed by EDM process and simultaneous EDM ECM process, where you can see the better surfaces. Okay. Now, simultaneous EDM ECM process also have one beauty, that is called, the ceramics are partially conductors, they can also do on ceramics also. So some of the ceramic machining that you people are looking at, if you are looking at, you can try in our machine, is subjected to if there is a partial electrical conductivity and so on. These are the proofs that we can say that these are all done on the ceramic materials, powder compaction ceramics, which we have slightly conductivity material that we put and we can try to do it. So hybrid micro machining, again I said EDM milling of master molds, where you can develop any type of molds. You can see the micro channels here, how the micro channels are made, and for spin rate for the electro spinning of nanofibers and other things also can be made. Micro attachment, you can make very good gears and so on, so that you can use for multiple applications. At the same time, micro wire EDM is a very good attachment. However, our machine don't have that one because we have Agile Charmil is 80 lakhs separate wire EDM system is there. That's why we have not gone for an attachment in wire EDM. Okay, so you can also make array of electrodes for heat sinking applications and so on. So another one which we don't have definitely is diamond turning, and which we are looking at is a diamond turning process or a standard rigid machining process, where you can have a drive which is ultrasonic elliptical vibration device. So now the question here is, this is the system that you are seeing, practical system. This is a schematic that I am going to do. So how do this machining will happen is this like of electrical. It goes and comes back. It goes and comes back. Because of that, if you can manipulate how fast it can do and how fast you can rotate your workpiece and feeds and other things depend on that, you can generate not only the micro features but also very beautiful micro textures also. Okay, these multiple compound eye surfaces and other things are frizzle lens arrays and other things are, you can make very fine. And most important advantage is, my tool is in contact with only for some time and it will come out. So when it come out, what will happen, you can properly cool it because it is not in touch with respect to the workpiece material. That's why it is very good that you can do a better machining process and your tool will have a good tool life. Okay, hope you understood what I mean to say. For example, this tool goes here, when it touches here, then only the machining will take place. Again, 90% of the time it is in the air. When it is in the air, if you are supplying a diamond, say cutting fluid, so it will be properly cooled. Okay. At the same time, even though you are not using the thing, it will be cooled because 90% of the time it is in the non-contact. Only 10% time or 15% of the time it will be in contact with respect to the workpiece material. So that is the beauty about ultrasonic elliptical vibration device. Nowadays, many people are working on different type of vibrations on it and other things for generating a lot of structures. So lasers, as I said, we can do lasers texturing with an overlap of 0%, 25%, 50% overlap and other things to make hydrophobic surfaces, hydrophilic surfaces. These are all our regular duties on biosurfaces basically for texturing and other things. Those people who are interested, they can come down. And we also do laser micro machining. As for laser micro machining, again, before I take to my original work on microorganism space micro machining, this may be the last one where I would like to tell you that when you have a lasers follow the Gaussian beam distribution. So when the Gaussian beam distribution is there, what will happen? At the center, there will be high amount of heat will be there. As you increase, say as you go from one hole to another hole, what will happen? The previous one will experiences the room temperature. Because of that, the basic material removal mechanism of laser beam machining is melting and evaporation. So melting and evaporation, so only melting and evaporation takes place at the center. At the edges, the melting will take place, evaporation will not take place. When the evaporation is not going to take place, in that circumstances, the laser is moved from one place to another place. Because of that, what will happen is that unvaporized material will resolidify. That's why a molten material which is melted by laser unable to evaporate, that will resolidify. Because of that, what will happen is that converts into recast layer. So how the recast layer look is like this. Okay, when we are doing a laser micro machining at the center, because the lot of power is there at the center, so melting and evaporation takes place. At the edges, melting takes place and evaporation will not take place. Because of that, what will happen? The molten material will resolidify. This resolidification, that's why it is called recast layer. So what do you mean by casting? You have a molten material which you put into a mold basically. So there is no mold, but molten material resolidifying. That's why it is called recast layer. Okay. So now these type of drug eluting stents require a lot of micro machining applications on a nitinol stents and other things. So what is the application? It has to be eluted properly or released properly. If your surfaces are like this, there are three types of problems. One, this recast layer may dislodge from the place and may cut the arteries. Two, the metallochemistry of the drugs that predominantly used here will be designed for the parent structure, not for the oxide layers or the copper layers. Third one is it will not elute as per the required amount, because or it is not going to release as per the required amount because the surfaces are not smooth enough. So you need to do not only the micro machining but also do the finishing of these micro holes. That's what we have done, and you can see with respect to our mediums basically. So as I said, we are extensively works in the area of nano manufacturing or nanofluids based manufacturing and other things. So we have our own technology. So commercial are very very expensive, and we have almost all 1/10th, or you can say 1/9th of that one we have. So those people who are interested, they can contact us for polymer rheological abrasive mediums for nano manufacturing. Okay, I'm not going to talk. If anybody want, they can ask me. Our medium, whenever you are going to impart some temperature to it, because our system has temperature controllers, and you can change the viscosity from high viscosity to the low viscosity, so that today you are finishing a big holes, tomorrow you can do finishing of small holes and so on. So that's a beauty about that particular process. So that's what you can see here, these holes which are manufactured by microEDM process. So globular structures are there, micro laser process, both are thermal process only. So you can have similar type of structures, and then you can do the finishing of these particular surfaces so that you can get surfaces properly. I mean to say surface topography properly, as well as surface metallurgy also, because at last you should target about what is meant by surface integrity that you have achieved on the surface. In that circumstances, you should also not only look at surface morphology, but also you have to look into the surface metallurgy aspects also. Okay, so that's how we do finishing of this drug eluting stents and so on. Okay, so apart from it, as I said, we can also do the finishing of fuel injector nozzles. So fuel injector nozzles, if the surface is very very rough like this, what will happen? This particulate recast layer may enter into the chambers and may destroy, because these are all hard particles and other things. Second, if you do polishing by these particular fluids, you can also get not only the deburring, but also you do radiusing. For example, if you have a micro drilling process, at the bottom side you have this type of burr. When you use this medium, you will also not only deburring process will happen, but also you can do the radiusing and so on. This is a system that we have at IIT Tirupati for nano manufacturing, which we make as a smart manufacturing system. And this thing here, I'm not going to talk. This is the front view and this side view of the system. Now I am coming to the topic, because so micro machining using microorganisms or bioorganisms. This is the one that we are very fortunate. This is the overview of what I'm going to talk now in next couple of minutes. Before that, I would like to say that we got the best paper award for this particular work at IIT Madras. Okay, so we got the first best paper award. I mean, say first position, second position, third position. So we got the first position award. So what is the beauty about this particular thing? What's the beauty? So Vision 2050 or Vision 2047 or whatever may be the targets that the people are targeting about sustainable manufacturing technologies. So one of the extreme angle of sustainable manufacturing technology is zero waste manufacturing. I mean to say, when you have a manufacturing process, you should not develop any waste. That should be the target. Okay, so in this particular process, what we are doing is, we are, for example, I have a micro nozzle here, or a micro mixture here. Just two examples are there. Whether I take a micro nozzle or a micro mixture on a copper plate, I can do by lasers. Because as a mechanical engineer, first and foremost thing that I can do is lasers. So what will happen? First and foremost, on a copper, because of its reflectivity, the performance will be less, but however, you can achieve. There's no problem about it. Either hook or crook, you can get it. But in a laser micromachining process, the material removal is by melting and evaporation. So that wherever the laser falls, material is going to melt and evaporate. That means that something is going to the air. Maybe environmental pollution may cause and other things, doesn't matter. Okay. The second, if I use this particular micro machining using biomicroorganisms, the same photolithography if I can do, okay, masking and other thing, and I can release these organisms because of its biological leaching action. This will leach out molecule by molecule or atom by atom. Because of that, what will happen here is that not only you are getting a microfluidic channel, but also you are getting a copper micro nanoparticles. So in the previous case, any thermal or mechanical micro milling you take, micro electrical discharge milling you can take, or lasers you can take. On all the conditions, whatever I am doing the machining process, I am generating the waste. Simple example is micro milling. For example, if I do micro milling, I get chips and I need to throw it out, or I need to recircle also. Okay, so here I'm getting copper nanoparticles, which are very, very expensive in the market. So as a mechanical engineer, I'm getting microfluidic channel. At the same time, as a material scientist, I'm getting a copper nanoparticles. How I am going to get? I'm going to talk. Okay, this is how the laser make. So whenever you see here in a laser micromachining process or any type of process, you have a recast layer, there will be undercut, there will be tool wear, there will be a heat affected zone. And for example, if you are doing by electrochemical machining process or something, you need to dump those electrochemical or electrical discharge machining. Also, you have a dielectric fluid, you just need to dump into the nearby water body. So these are all causes lot of problems. Okay. So now you can see here, micro machining can be normally done by mechanical, optical, chemical, and other things. However, you have a lot of problems. Either create damage layer like it affected zone, and either you need to contaminate the environment, or whether you may be experiencing high amount of forces because micro milling and other things. And potentially these channels, the chemicals that are using may corrode away the surfaces also. Okay. And these are all will increase the production cost, and so alternate methods are always required. Okay. So now bio micro machining. So just simple. In a conventional manufacturing, all we think that my cutting tool should be much harder than workpiece material. No. When it comes to advanced machining process, you can do a titanium or a hardened steel with copper, where copper hardness is much, much less than hardened steel. So that means that the rule of conventional manufacturing, where you say that the tool should be much harder than workpiece, is eliminated now. So the micro machining uses the bacteria as tool for material here. So this is Acidothiobacillus peroxidans, which is a common bacteria for biomicro machining. And this gains energy by oxidating of bivalent ions, normally ferrous iron, and to trivalent iron. So that is Fe3 plus and Fe2 plus. Normally, there is a mechanism inside the body. So again, like Bahubali movie or any movie, whenever you see that, you just see, we are not killing any animals. So we are not killing any animals here because the acidotibacillus peroxidans are removing this particular material by its metabolic action, not by sacrificing their life. Okay, how is that? I am just explaining you oxidation of Fe2 plus to Fe3 plus. So since the bacterium is very small and it appeared to be ideal tool for micromachining because it is okay. So now you can see here many surfaces, corrosion surfaces are something. So corrosion is what we don't want because there is no stipulated direction, stipulated thing and other things. Okay, however, this is also a leaching process. Okay, it's a chemical leaching process. Whatever we are going to talk biomicromachining, the biotechnologies speak in terms of microbial leaching or bioleaching. So if I can control the leaching by the microorganisms, that is nothing but my biomicromachining process. So cell culture and metabolism, if you see here, first we need to get acidotibacillus peroxidans, which are normally colorless, rod-shaped gram-negative bacteria with polar flagella that you can see here. And if you do higher magnification, it looks like a rod shape and other things. And these are all when you go for higher magnification, like 30,000 or something, then you can see how this look like. These are acidotibacillus peroxidans. Why I'm saying peroxidans? Because I said in the previous slide that it will convert Fe2 plus to Fe3 plus and Fe3 plus to 2 plus. This is the mechanism that it will play a role. That is what you are going to see here. And here you can see. So how this will act as a biomicromachining tool. What is happening inside the acidotibacillus peroxidans? For example, if you see in a human body, in the stomach, normally you will have acidic in nature, am I right? 4 pH will be there. In the mouth, you will have almost all 7 or 7.2 pH, which is called normally a neutral pH. That's why even though you spit on anything, nothing will happen because it's a neutral pH. When we are culturing the acidotibacillus peroxidans, before you understand this, it may look like that some organisms I am getting and I am just putting on the surface and I am getting bioleaching. This looks very easy, but the most important task here is that growing these organisms, understanding the life cycle of the organisms. When assume that I have three people, one is 10 years old, another one is 30 years old, another one is 50 years old. So who will do better job? I mean to say same physical work. Normally a 30 years old guy will do. So that means that when my microorganism is at the right young age, its performance will be very high. So as a researcher, it is my primary responsibility to understand what is its life cycle and at which stage it is going to extract more amount of material or bioleaching will happen at the maximum performance. So normally around 20 days or something of the culturing, it will give you better results. This is what we found in the research. Okay, so normally if you see here, combination of continued oxidation Fe2 plus to Fe3 plus, normally this will happen in the cultured medium inside the body. So this is inside acidotibacillus peroxidans. So acidotibacillus peroxidans on the surface, it has a Fe2 plus. When it goes inside, it will react with oxygen and hydrogen and it will release water and Fe3 plus it will form, which is organism's continuous production of Fe3 plus. So this normally what will happen when you bring these organisms to the copper surface, what will happen? If this Fe3 plus will interact with respect to copper and it will make Cu2 plus, again it will be a Fe2 plus because it loses one and gives to that one. So because of that is the mechanism that you can see here. So inside the body, so this is the inside the body. What is happening, you see at the top, it is Fe2 plus, cytoplasm, inner membrane, periplasmatic sphere. Okay, this is the inner membrane and other things. You see here, it is exposed to the surface. Whatever the mechanism that I told, the metabolic mechanism, it has Fe3 plus inside the body, and this Fe3 plus will come and interact with respect to copper and forms Cu2 plus and takes out the non-oxidizing agent. Now you can see here, I have Fe2 plus which converts into Fe3 plus, which is there inside the body because of the acidic action. And this Fe2 plus, when it Fe3 plus which is formed will interact with respect to copper and form these ions and will leach out. So, okay, so this is how the mechanism, basic mechanism. Okay, these are all normally we take the support from the biological people. Okay, so if you can see here, azothiobacillus peroxidin is here. Inside it will have Fe3 plus which interacts with the copper and leaches out as a Cu2 plus, and when it becomes Fe2 plus will go inside the bacterium cell and again will react with Fe3 plus and comes back. That is the basic mechanism. So how do I control this one? So I need to design whatever the shapes that I want, and I need to do photoresisting like MEMS and UV expose. Then we develop the channels. These channels just you put inside the biomicro machining. So wherever there is an exposed area will convert this metabolic action, and this type of microchannels are generated. So this is how the micro machining will takes place. So normally, once you see, normally lot of parameters are there: machining time, temperature of the medium, and soaking conditions. So bioorganism concentration, purity of workpiece material, size of the microorganism. I said size of the microorganism plays a crucial role because child cannot do a better physical work or a old man cannot do a physical work. So only the young persons. So output normally specific material removal rate, surface roughness, channel dimension like curve width, curve depth, and other things. Any overcut is there or something, that also we will normally understand. Okay. So now you can see here with respect to time, cell density. So cell proliferation, cell density, as you increase the number of days, at 20 days or beyond that, what will happen? Cell density is the maximum. If the cell density is the maximum, what will happen? The more number of cells will takes place in the biomicro machining process, and it will take out lot of amount. Amount of copper leach that you can see here with respect to hours and with respect to cells per ml. As you can increase the cells per ml, what will happen? You see, the material removal obviously will increase, and as you increase the time of stay, because we are getting 20 days or something, then after that we are holding that a 20 days or 21 days organism for 40 hours or 50 hours. This is going to be the maximum. After that, what we have observed is slightly stagnant for some time after 40 hours in some cases, and then in some cases whenever you are crossing 50, it is reducing. So that means that the material removal mechanism is preferably you can keep for almost 40 hours with young things like 21 days or something. Now you can see here Micro nozzle application, I have a better surface, definitely. At the same time, you have purely the material, there is no carbide layers or oxide layers or something. So only small treatment is required. At the same time, you can also see the surface roughness is very, very good, almost all 0.3 microns. Now you can see the temperature of the medium. So normally temperature of the medium, if you are maintaining, what will happen? Self proliferation will be good basically. So self proliferation will be good even though if you see in when you have a fracture or anything. So self proliferation will be good if the temperature is slightly above the body temperature and other things. Okay. So material removal rate, you can see at 25 degrees, 30, 35, 40 and other things. Normally, the body temperature is almost all, should be maintained constant. That's why the humans also will have their body temperature of 37 degrees. So this also performs very good at 35 or other. Shaking speed. Why you require shaking speed? So the shaking speed of the workpiece and liquid is required because you are doing a dynamic removal of material. For example, sometimes organisms are removing, but sometimes the particles may not come out. So if you do slightly the shaking, so what will happen? There is a chance that dynamic action at the interface will take place and material removal will take place. If you shake too much, then gone case because sticking the organisms predominantly to the surface also is very high. So that's why we never gone beyond 250 or 300. So we have tested at 500,000 also, but the problem is the material removal drastically decreases because it is merely stick to the surface. Because if it the acidothiopenicillin peroxidants, if it is not sticking to the surface, this Fe3 plus will not convert into Fe2 plus and Cu2 plus. Because of that, what will happen? For that metabolic action or bio leaching has to be happen if the surface contact is proper. So you need to optimize your shaking speed and other things. Okay, cell density, as I said, cell density should be as near to the one. That is very, very good actually. So not only that, so micro machining is one thing. It's very good for micro finishing basically. So for example, if I want to do micro channeling and other things, then only you have to do the masking and other things. For example, you don't have that facilities. You have a turned surface or a milled surface or a grind surface. So complete surface you just put into the acidothiopenicillin for oxidants. What will happen? So this will eat away the surface, or I mean say by the metabolic action, and it makes the surface texture. Okay, so typical diamond surface finishing pre-biological you can see and topological of after 24 hours. It can generate a lot of textures on it, biological textures that you can produce. And not only about that, if you see a 48 hours long and other surfaces, you are going to get a nature inspired surfaces. So these nature inspired surfaces are very, very good for the biological action and so on. Okay. So apart from it, you can also see the micro gears, microfluidic channels that are can be fabricated on copper. Possibly one of the material that you can use is copper here, and we have tried with the wood. And at the same time, as I said, it is finishing also you can get. So for example, you see a ground surface, it has a lot of burrs are there, it has peaks and valleys are there. These are the surfaces when you just put into the acidothiopenicillin peroxidants predominantly, you can they can eat away all the surfaces that are exposed and you can get a very good surface. Okay, so those people who are interested, because this atal program, so repeatability of the process is less. So so you can work into repeatability. The biggest challenge this particular process is the micro machining time is very high. So can you overcome by any other means? Okay, so how can you reduce the time and increase the production rate? Second thing, people are here talking about very less forces. Can you interact with respect to acoustic emission on the surface and get the forces and other things? That may be another good exploration that people who are looking at PSD and other things. So any source of material removal other than leaching, for example, in the current case, it is a bio-leaching process. So like by grinding process, you see there are multiple material removal mechanism like micro cutting or shearing, ploughing, rubbing, this type of things. No, this type of things can be observed here also. If you go to micro to nano, and modeling of material removal anyhow is a straightforward. Those people who are doing in modeling, so can we apply for any type of heterogeneous material or a composites and other things? So control is in the motion of the microorganisms by giving certain paths for the workpiece material or something, vibration or something that is. So these are the some of the questions that I have, and we are also addressing. So if anybody is interested, they can come and work with us. Apart from it, we also work into soldiers. As I said, now body temperature is 37 degrees. We also work into some of the bio gels for micro machining applications. It's not only about micro machining, we also work into micro 3D printing, where we have Luminix Plus at IIT Tirupati. These are the microfluidic channels that we can generate, and very complex microfluidic channels that you can generate. This machine looks very simple. This cost you like 30 to 40 lakhs rupees. Okay, and we have you can also generate these type of channels, whatever the channel that you want, which is resembles like a human body or something, and you can generate. Okay, so these are the some of the capabilities of Luminex Plus, which we have at IIT Tirupati, and we are working closely with respect to our Ayurvedic Medical College. We are also working with Sanskrit Medical College with respect to all these things. Okay, and fortunately we have ICER also. So this is how microfluidic channels, not only about machining, but also you can print it. These microfluidic channels using Luminex Plus. And you can also, you can see this is the one that we have done at IIT Tirupati for the non-linear applications, non-linear microfluidic application that we have done. Okay, so thank you one and all. And as Professor Parida says, I'm also handling general of manufacturing process, where my domain is grinding, abrasive process, rheology, tribology, and abrasive based machining and fluid flow. I mean, say abrasive fluids and other things. This is my domain. So those people who are interested to submit your manuscripts, please submit. Subjected to, if you have a good science, definitely you will get into our journal. And hopefully, I see more and more publications from India. And I wish you people can submit with a good science, not that somebody did on mild steel, I am doing on copper, somebody did on copper, I am doing on brass. No. So keep more into the science part and do very good research and other things. Okay. Otherwise, our acceptance ratio is very less. Okay. So our acceptance ratio is normally 6 to 8%. These are the facilities that we have at IIT Tirupati. Now you can see abrasive flow finishing, 8-axis laser micro machining center. We have micro machining center DT100i. We have a drag finishing system. We have a finishing station. We have a rheometer So and 10 par MC 302 is there, and Bioluminex X bioprinter is there. Contour 3D surface profile emitter. We have filament makers. We have ball mills for powder making, micro to nano powders. We have ceramic 3D printers, MQL systems, DMG Mori turning, DMG Mori CNC milling, metal 3D printer. We have EOS 290 and tribometers. We have at the same time we have Viridium from Agail Char millis and so on. So these are the things that I have told you. We have metal 3D printers, ceramic 3D printers, and polymer 3D printers. Post processing of additive manufacturing components, 3D surface profile emitter from Broker is there. Pyridium from Agile Char Millis, TMG Mori milling gate is there. High speed cameras we have. Those people who want to use, they can use. And IR camera for temperature, ranging from 350 degrees to we have up to 2000 degrees. Micro nano indenter is there, and XRD, powder XRD is there, thin film XRD is there. CMM, coordinate machining machine, many you may have one out of roundness tester. PVD, as I said, we have our vector sputtering and pulsating DC. Tribometer, we have rotary, reciprocating, and butterfly. Butterfly is for biotribometer. And high temperature keep fatigue testing is also there. Some of the facilities which are I'm going to talk is arrived. Some of the facilities are yet to arrive. 3D filament makers we have already. We are working. So we are making composite filaments. Those people who want to do composite filaments, they can approach us. We are giving to many customers this composite filaments like PLA copper, PLA stainless steel. So all people talk about copper, carbon fiber, glass fiber, and other things. Variety, what we try to do is we try to give them with the metal particles so that no your publications will be very fast and you make a degree at the earliest. Micro machining center arrived already. Laser micro machining center we have. EDM, which we are yet to procure. FESCM is about to come. So which has EBSD, EDS, lithography, and we also have STEM for biological applications. Atomic force microscopy is going to come, and PPMS, which is most costliest equipment, physical property measurement system, about 18 to 20 crores. XPS is about 6 to 7 crores. HRTEM is a second costliest system, high resolution transmission electron microscopy. Normally range is like 15.5 crores or something. LIPS we have laser induced breakdown plasma spectroscopy, DSCT, GA, we have bioincubators and in vitro laboratory. Some are there with us and some are there in ISER. We have ISER and ISE adjacent each other. Creep and fatigue testing we have, and friction state processing we have. We are looking for summer interns who can stay more than 6 months, not 2 months. So those postdoc students who want to apply with facilities, partially suppose somebody want to do their BTech work more than 6 months, MTech work again more than 6 months. Below 6 months or 5 months, there is no meaning in coming because you may not learn and you may not to contribute. And some of the PhD students who want to do a partial their experiments, they are most welcome. So with this, I am very thankful to all the funding agencies from I started my career at IIT Guwahati with 5 lakhs, then Baba Atomic Research Center about 23 lakhs, then DRDL about 75 lakhs, and DST, TSDP about nearly 1 crore, DIT, which is now MIT, about 60 crores. Then we have Imprint 3 plus 3 crores with IIT Kanpur and IIT ISA Bangalore. These are the things completed, and just closed projects are like SARB special about 45, BIRAC that Galuting State project about 41, then SARB about 32, and I'm a IGSTC Indo-German Science and Technology Center. So we have 6.8 crores project, under 2+2. There are only 5 projects that they have given. Okay, so one of the projects that we are the people. These are the recent projects. Respond of ISRO about 32 lakhs, STI, DST about 61 lakhs, small project about 56 lakhs. These are the CARS project, DRDL 17 lakhs which have completed. Now 42 lakhs we have received. So almost all we have 42 plus 17 means, yeah, 50, 60 lakhs. We have consultancy from DRDL and power grid we have. Apart from it, we have a TAH Precision Technologies and Positioning, where I do look at precision manufacturing. This particular center is about 120 crores. Okay, this is one side. Another side, the students. I am just a front face. Yeah, so the lot of hard work goes into the laboratories by the students. Okay, with this, thank you. I think I'm on time to have certain time for the questionnaire and other things with that. Thank you. Thank you, Professor. I think all people are tired.
Sir, good evening, sir. Hello, is my voice audible? Sir, Ravi sir, that is a very nice, wonderful presentation, sir. We got lot of insights on micro machining and nano machining. Application of microorganisms will enhance the machining process. Sir, one thing I'm much more interested in the composite filaments, sir. Said, it will be available with you people. Uh, May I know the percentage, sir? PLA in copper, what is the metal percentage that are elements available with you?
Can I answer? So, as per your requirement, we'll give on demand. We don't have any specific requirement. For example, some people they are getting is see, if they want to plot 5 points or 6 points, they say that's 0, 2.5, 5, 7.5, 10, 12.5, like 15 or something. They will ask and we will give you.
Okay, okay, sir.
So that now they can make the tensile coupons, they can make any coupons as they increases, whether it is increasing, or there are people who want up to 20%, there are people who want up to 30%. We don't have any problem. So you tell us, because no person will produce in India.
Yeah, sir, that is the thing.
The thing is that no one uses these type of particles. You just tell what are particles that you want, what are the filament that want you want, PLA, PEG, or ABS, and some people also want PTFE. So you have ultra high molecular polyethylene. Many people have many materials, and you just, for example, many people want PLA with copper because PLA is a bio and copper is antimicrobial, or
Yeah.
brass. So brass is again particles will have a lot of things. Yeah, so it is on demand.
Okay, sir. A simple mail to you for communicating. That is enough, sir, for
Yeah, you
raising the query.
can. I have showed my mobile number. You just contact that. That will be fine.
Ah, okay. Okay, sir. Thank you, sir.
So this is my word 86383938. This is WhatsApp and call. The second one is not working. This one, just so you can use that one, but don't share to the students. Yeah.
No, no, sir. I won't say students. Okay.
So many people nowadays they're asking actually that. So you have to come through proper channel through the institute, because the equipment and other things are belongs to the institute. So we will charge as per the guidelines of the institute.
Definitely, sir.
Okay. So any type of filaments, for example, some people want ceramic actually, like silicon carbide particles. We are giving silicon carbide particles also.
Okay, sir.
So some people nowadays they became too much intelligence. They are want copper plus silicon carbide, copper plus hydroxyapatite. See, hydroxyapatite is a bioceramic.
Yeah.
Copper is antimicrobial and PLA. So people want ternary composite, like one metal, one ceramic, one polymer. So they want to publish very fast, it seems. So
Okay, sir. Thank you very much.
you can ask me. I don't understand. What do you mean by jet? What do you mean by jet holes?
Sir, good evening, sir.
Yes, sir. Please, sir. You
Sir,
are from
shall we
which institute,
shall
sir?
we use the hot air to finish the jet holes, sir?
What is jet hole? I'm not getting you.
Jet holes, sir.
What do you mean by jet hole? I don't know what is which jet you are talking about.
In automobiles, we are using the jets now, sir. Fuel jets. Sir.
Fuel nozzle holes. See, this all
Yes.
depend on what is the melting point of that material. No?
Sir.
So, for example, if you send hot air, what will be the temperature? Normally, maximum 100 degrees.
Yes, sir. Maximum more than 100 degrees like that.
Assume the 200 degrees. Assume. So, where the
Yes.
melting point of the material is, assume that normally H13 tool steel.
Sir.
You know that it will be more than 1000 degrees. I don't know whether you can make it
Uh,
because the melting point is far away, no?
yes, sir.
So, but you can do for polymers, not for metals, maybe. That is my
Okay,
thought
okay, sir.
process.
Soft
Because
metals will pass.
polymers, it may be possible.
Uh, okay.
So, you are from which institute, sir?
Sir, SSID, sir. Sai Institute of Technology and Science, Raichoti.
Oh, okay. Okay.
Yes, sir.
So, Maurul.
Yes, sir.
Yeah, okay.
Thank you, sir.
Sir, the speaker has left, sir, just now. Sir, yes, sir, yes, sir. I think the previous speaker has left, sir. We should next session now. Yes, sir. Yes, sir. I'll take. Yes, sir. I've taken some snaps.